we have to move to our next talk. It's my great pleasure to welcome our next speaker, Professor Nich Huggett. Professor Nich Huggett is a distinguished professor at Department of Philosophy of University of Illinois, Chicago. His research interests are the philosophy of science and philosophy of physics. Professor Huggett has published widely on philosophy of physics, papers and books. Among his books, there are Everywhere and Everywhen, Physics Meets Philosophy at the Planck Scale, and more recently, Out of Nowhere, on co-written with Chris Wuttrich on the emergence of space-time from quantum gravity, and also Quantum Gravity in Laboratory, co-written with two other authors. Professor Huggett will tell us about ways of branch making. And nice to meet you, Nich. Again, the screen is yours.
Hi. How do I progress through the slides?
I guess you have to click on the 3-point icon at the top right corner of your screen, and then management of slides, I guess. Do you see the 3-point icon on the top right corner?
Take ownership. No?
Yes.
Oh, what a great system. Okay, very good. Oh, this is very nice. Thank you. Thank you so much. I wish I could see everybody. Is there a room full of people that are there as well as people online, or is everybody online?
It's everybody online, yeah.
Ah, okay. Well, good morning, everybody. And it's nice to have my first time in Iran.
Thank you, welcome.
A country I very much hope to visit one day. So now I lost. Oh, there we go. Yes. Okay. So I know we're the time is the clock is ticking. So let me get started. So I'm going to talk today about a topic generally within the framework of the many worlds interpretation of quantum mechanics. It's work that I've been doing in the last few months, mainly at the University of Bristol with James Ladyman there, and a graduate student, or just about to finish, Nadia Blackshaw, also there. It's joint work. It's based on joint work. That what I'm going to say today is coming from that I've written. So the specific things I say are down to me, but it's all based on ideas we developed together. So although it's going to be about many worlds, as I'll explain, I'm actually not going to, I'm going to try and stay clear of interpretational questions. I'm really going to talk much more about how far we can get towards a many worlds view just within quantum mechanics. Then one could think later about what else had to be added to actually get to a many worlds view, as you'll see. So ultimately, what we're going to get is not many worlds, but many branches, and I'm going to try and distinguish those a bit for you. Okay, but let me get on and sort of explain. So we're based, the work is thinking about the ideas developed by various people, but most sort of fully by David Wallace in his book, The Emergent Universe, which is a defense of a many worlds interpretation. But we wanted to understand some things about the physics that's going in, that he's relying there, and try to kind of, there's some things we felt could be clarified with a very nice, simple model. So I should say, sort of in a sense, there's very little, there's not much that I'm going to say today that David's book, but I think it's going to give you a very nice kind of concrete situation in which you can see what these ideas really amount to in a way that he doesn't do. So, okay. So here's a quotation from the book that'll get us sort of moving and get us towards an issue we want to address. As we would expect from the absence of action at a distance, then, branching is not a global phenomenon. Rather, when some microscopic superposition is magnified up to macroscopic scales, it leads to a branching event which propagates outwards at the speed of light of whatever dynamical interaction is causing decoherence. In practice, it propagates out at the speed of light. So I guess I should have said I'm sort of assuming that the audience has some awareness of what the many worlds interpretation looks like. In many sort of basic presentations, there's a measurement and the world splits into as many worlds as there are different possible outcomes for this experiment in quantum mechanics. And one sort of has a picture where the whole world all splits at once in some way. And the important point here is that's not the idea of branching, which I will explain, we'll be unpacking, leads to a more dynamical, quantum mechanical sort of picture of what's happening in the creation of worlds. That's what I'm trying to elucidate for you. And in particular, because the branching is just an ordinary quantum process, it's subject to the laws of quantum processes, and those, if the world's relativistic, those are causal. Things effects propagate at the speed of light. So branching must be propagating at the speed of light. And really seeing how that is what is in some ways the main topic of the paper. So the one sort of puzzle we sort of had when we were thinking about this, I mean, these things must be compatible, but we really wanted to see explicitly how local propagation of branches is compatible with what we know about quantum mechanics and its non-locality due to, well, as exemplified by violations of the Bell inequalities, for instance. I hope to sort of give an explanation of that. And as I've sort of been saying, the method by which to address this question and elucidate this picture has been to give a very simple model. Its simplicity means that it really illuminates very clearly certain features of branching in the Wallace account, but by its simplicity makes those things clear, but it also comes at the cost of excluding and just really not saying anything about other features of branching. So there'll come a point in the talk where I explain that a bit more. And the general stance that I'm going to take here is going to be neutral, or fairly neutral, on the interpretation of quantum mechanics. I'm really just going to be looking at the effects of unitary evolution, so ordinary sort of quantum mechanics and ordinary kind of quantum mechanical thinking. But I'm not going to say exactly what we should make of branches. Obviously, Wallace wants to say they correspond to different possible worlds, but I'm going to stop before we have to answer that question, or as you'll see, more or less stop before we get to that question. So what I'm really assuming here is that we have quantum mechanical unitary evolution. So I'll point out that means that what I'm going to say here should be pretty much compatible. Almost everything I will say will be compatible with no collapse theories, and that would include a Bohmian hidden variable kind of theory, because that has the unitary evolution, but it adds some more to it. But I'm not taking a stance on that. Collapse theories won't be compatible with what I'm saying, except collapse theories, the collapses aren't instantaneous. They tend to depend on how many degrees of freedom, how many atoms that are involved. So even for a collapse theory for short times or for small systems, what I'm going to say will be relevant. Okay, so I'm going to tell you that the upshot is to sort of the first part is going to be to say what branches are, and then a little bit, then the question of interpretation would be, well, what do we make of these branches? Okay, so yeah, these are the steps of the talk. I'll give you the model. I will distinguish entanglement from decoherence. I'll distinguish decoherence from branching. Then I'll talk about the idealizations, what the model does and doesn't show or illustrate. Then I'll come to the question of non-locality with which I set things up, and then draw a few lessons, or really summarize the lessons by that point. So here's my simple model. And really it's about so what we want to do is think about how branches are created and how they spread in the way that the Wallace quotation indicated. So we really thought and just really started writing down the very simplest model that you might kind of imagine to illustrate these things. Really, we got to first of all think about, we want to see how entanglement can spread in a system. So we need a spatially extended system with degrees of freedom located in different places, and so they can become entangled in as time goes on. So the simplest case thing you might think of is, imagine we have just one spatial dimension, and suppose that the points in this dimension are in fact discrete. So we have a lattice, and we'll label them, we'll assume it's a half line. So we'll label the first one 0, and then 1, 2, 3, 4, and so on to infinity. Okay, there's going to be a system, which is the thing that is going to, in the first place, be decohering, and that's going to be a qubit, and we'll put that at the x equals 0 node. And let's suppose it's a qubit. That means it's a two-dimensional system. It has states 0 and 1, and ignoring normalization, which won't affect anything for us, let's suppose it's in the state 0 plus 1. So it's an equal superposition of being in the state 0, and being in the state 1. We also, for this kind of story, there's a system, and it interacts with an environment, and that produces entanglement, which produces decoherence. So we need an environment. And for that, the simplest thing one can kind of imagine is at each one of them, the points 1, 2, 3, 4, and so on, there's going to be a field that can take on two values. It's quantum mechanical. So two-valued, well, qubits are two-valued, but just to keep things straight, we'll think of this as a spin-half field. So at each of the other points, there's a field whose value, in this basis, can either be up or down. Obviously, superpositions would also be possible because it's quantum mechanical, but this, yeah, okay. And that will arise as we go. Okay, so we suppose that there's such a field at all the other locations, and let's suppose the initial state for the environment is that all of those are in the up state. So I've kind of now pictured my qubit and then the field where everything is up. Remember, the qubit initial state is in a superposition of 0 and 1. Okay, so that's the model. We need to, obviously, to show how branching propagates and to apply unitary dynamics, we actually have to specify what the dynamics for this system is. And we're just going to give it by hand. There's a full unitary evolution that I could specify, but I'll just tell you the relevant parts. So first of all, we need to know how the qubit interacts with the field. And because we want things to be local, we want this to be a nice model of what happens in relativistic space-time, there's only going to be interactions between neighboring nodes. So 0 can interact with 1, 1 can interact with 0 and 2. Each node can only interact with the nodes next adjacent to it. So the qubit can interact with the field, the field degree of freedom at node 1. And here's what we're going to specify. I don't have any, I don't have an equation of motion in the back of my mind. I'm just stipulating how what the interaction is. So if the qubit is initially in the state 0 and the field is initially in the state up, then after the interaction, the qubit will still be in the state 0, but now the field will be in the state down. If the qubit is initially in the state 1 and the field is initially in the state up, then afterwards we'll have the 1 up state. So you can see the field, well, you'll see the field then is, as it were, recording the value of the qubit. A down means, well, the qubit was 0, and up means, well, the qubit was 1. Okay, so given our initial state, which was 0 plus 1, and then the field in the state all up, we apply this. You can see we're only interested in the leftmost of the field states, which is up. So the 0 up goes to 0 down, and the 1 up goes to 1 down. And so after this interaction, we imagine at the first time instant, this interaction takes place, and then the state will become 0 down plus 1 up, and the rest of the field is still in the up state. Okay, similarly for field-field interactions, and these will be the same anywhere, but if an up and two adjacent up states, field states interact, then they stay both up. But if a down on the left interacts with an up on the right, then they both end up down. So we'll take the state that we just produced just above. And now imagine at time 2, we apply this interaction. Then the result is going to be, so again, on the left-hand side, I just wrote the state from the right-hand side above. We imagine at time 2, the field-field interaction occurs between the field degrees of freedom at 1 and 2. And so what we're going to get is 0 down down plus 1 up up, and then the rest of the field is still in the up state. I should have put some dots. You have to imagine that in these equations, there's ups going off to infinity here. If I did it again, clearly the next state's going to be 0 down 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 plus 1 up up up, tensor product with an up, the rest of the field in the up state. And so at each time, another field degree of freedom will become entangled with the qubit. We'll get down correlated with the 0 and up correlated with 1. So I know the equations can get quite long, so I just drew a little picture of it. So my initial state, the very first thing I wrote down, I'll write like this. I have my qubit in the 1, 0 superposition and the field all up. By the way, this works better if the slides weren't sliding across, but we're just replacing one another. So I'll try to imagine that's what's happened. But at the next time we're at this state, I've got a superposition of 1 up plus 0 down, and then the rest of the field in the up state. Then, of course, at the next time, I have 1 up up plus 0 down down, the rest of the field in the up state. Then I have 1 up 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 plus 0 down down down, the rest of the field in the up state. Don't worry, I think this is the last one, and so on and so forth. This is what's going to happen as the entanglement spreads. You just get a bit larger and larger. The qubit is entangled with more and more of the field. Okay, hopefully that's the last one. Yes. So I'll leave that picture at the bottom. So entanglement is the sort of underlying mechanism for the formation of branches. But really, we need more than entanglement. Branches also rely on the idea of decoherence. So what is decoherence? Let's say this. So we've got entanglement, we want decoherence. Well, there's various ways of thinking about what decoherence amounts to, but here's one we'll talk about for now that'll be useful here. And the decoherence is the loss of quantum interference in a subsystem. Okay, so suppose I have a single particle and it has its wave function. Hope you can see my hands, is a wave packet that's over here in space and a wave packet that's over here in space. As long as they're not overlapping, there's no quantum interference. I mean, they're waves. But if they come to overlap, then like waves, you have to add them up, and then you take the mod squared to get the probabilities, to get the probabilities, and we'll find quantum interference. I mean, that's the whole. Well, it's not all of quantum mechanics, but it's the it's the interference part of quantum mechanics that exists even for a single particle. Okay, I have packets. Well, if they overlap, we get interference. Of course, we can think of this as the two slits. If my two slits are the two-slit experiment, if my two slits are a long way apart, so the packets never overlap before they hit the screen, then I don't get any interference. It's exactly if the slits are close together, so the packets come to overlap, that's what's going to produce my fringes. All right, so it's the loss of quantum interference, and quantum interference means, in this sort of picture, overlapping wave packets. So let's think that through. So suppose we have a pair of particles in one dimension, and now I'm kind of imagining, just imagine space to be continuous for this point. So I've got particle 1 and particle 2. So this is going to be their configuration space. And suppose particle 1 has a state that's composed of 2 packets, those little blue blodges at 2 different points in space, and they're not overlapping. And particle 2 also has a state that's composed, has 2 non-overlapping packets. Okay, I have to draw an axis for each one of the particles, even though I emphasize there's only one dimension in space. For quantum mechanics, we have to draw the configuration space to write down the wave function. This is the right space for writing the wave function for 2 particles, each of which lives in one-dimensional space. And suppose these 2 particles are entangled. So suppose the state then looks like this. Okay, and you can see in the configuration space, it's really the purple dots that represent the 2 packets that constitute the wave function for this system. The one in the top right-hand corner clearly projects down onto the blue packet for particle 1 on the right, and projects across onto the upper packet for particle 2. So this satisfies what I've described. We have an entangled system where each of the particles has a wave function that has 2 parts that are non-overlapping. So I think, right. So in the fancy slides, I have a little animation here to sort of show to think about this. So what I imagine is if I had one particle, as I said before, if I only had particle 1, if the blue packets moved together so that they overlapped, then we would expect to see characteristic quantum effects. We would have interference. But let me see what happens here. Good. Suppose I bring the 2 blue packets together. I move the 2. I play with the system so that the 2 wave packets for particle 1 now overlap, but I don't do anything to particle 2. This is the situation that I now get. So if there was only one unentangled, if particle 1 was not entangled with particle 2, I would now be seeing quantum effects. However, what counts is whether those purple circles overlap, and they don't, because particle 1 is entangled with particle 2, and because particle 2's packets are not overlapping, I won't see any quantum effects. Okay, so in that sense, it's because of the entanglement, which now means the wave function lives in configuration space. If I want to get quantum interference, I have to make the wave packets of every single system that's entangled overlap, and generally that's not what's going to happen. So what we've just seen is even if the packets of particle 1 are made to overlap, as I've just illustrated here, there now won't be any quantum interference, because quantum interference requires that the wave function in configuration space, the purple dots, overlap, and they don't. If we want to see quantum interference, we're also going to have to make particle 2's wave packets overlap. If we move the red dots, the red blobs down to the center as well, so they overlapped, then the purple dots would be overlapping and we'd get quantum interference. Okay, so, but that unless then is really crucial. If we cannot interact with particle 2, if we cannot make its packets overlap, well, either we decide we don't want to, or perhaps we're technologically unable to do so, or perhaps these things are space-like separated, or various other kind of reasons why we, in some sense, cannot make interact with particle 2 to recover the quantum interference, then particle 1 no longer behaves like a quantum particle. There's no quantum interference, and that is the condition under which we say it's decohered. Its probabilities are going to go back to being purely classical. We're not going to get those quantum interference effects. Okay, I mean, I should say this sort of explanation came out of sort of work in the 90s by David Albert and Jeff Barrett, and I'm just kind of repeating their sort of story about decoherence because I think it's a very nice kind of clear picture of what's going on. But the bottom line is decoherence is entanglement, okay, of two parts of a system, such that in particular, one of them cannot be controlled. Particle 1 in my example has decohered because it's entangled with particle 2, and I'm imagining I don't have any control over particle 2. Or if I don't have any control over particle 2, then particle 1 will be entangled. I've sort of said here, we do have the case that one can be controlled. In my model, I was thinking that I can move the blue packets around and I can't move the red packets around, but the can part's not so crucial here. So it's really important to think of decoherence as a relation between two parts of the system, one of which we can call the subsystem of interest. The other part we can call the environment. It's a relation between those, but it's always relative to some set of operations, what it is you can do to the parts of the system. Okay, so it's a relation between particle 1, particle 2, and the operations that we just have on particle 1, so we know we can't do anything on particle 2. If instead I became able to manipulate particle 2, then particle 1 would no longer be decohered. So it's very important that relation is relative to a set of operations as well. All right, I've gone a bit slow. I need to kind of pick it up a little bit. So the rest we can go fairly quickly, I think. So So with that in mind, let's specify that we can control the qubit. We can move that around as we like. But we can't manipulate the field in our example. So that fits with that being the environment. So it's maybe a little artificial in our model because, well, we just have a spin degree of freedom at each node, and maybe we sort of thought we could do that. But remember, this field is, say, representing the electromagnetic field, in reality, in sort of realistic cases, which has a degree of freedom at every space-time point. So it has infinitely many degrees of freedom. And the general thing that's going to happen here is they're all becoming entangled all over the place. This is spreading out at the speed of light. There are just so many degrees of freedom becoming entangled so quickly that we have no hope of manipulating every single one of those back so that we can recover the interference for the qubit. So we'll specify with what we've just said in mind that we can control the qubit, making it a subsystem of interest, but we can't control the field, so that's the environment. So by that reasoning, by the time, once the qubit started interacting with the field, and maybe after 4 units of time, so we get to the situation that's pictured, the qubit is entangled with the field. We can't control the field, so by our reasoning, the qubit is decohered. So that enables us to say that the qubit, at site 0, where the qubit is, branching has occurred, and there are two, let's call them local branches, because they're just at a point. There's the 1 branch and the 2 branch, in virtue of the decoherence. But more than that, okay, each one of the field degrees of freedom, each one of the nodes where you see a blue up and a red down, branch, that's also entangled, well, with the qubit, but also with the other field degrees of freedom, all the other red-blue ones. Each one of the nodes 1 through 4 has entanglement with all the other nodes, and as the thing spreads out, there's more and more entanglement between the nodes of the field. or more and more nodes are entangled, I should say. And so at each one of those nodes, there's also local branching. There's an up branch and a down branch. And so this is the key move to branching. We can now talk about extended branches. We can put together the branching at the qubit with the branching at each one of the other nodes, each one of the field nodes. Okay. There's a branch which is constituted by all the blue, and a branch that's constituted by all the red. So 1 up, 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 and 0 down, 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 down. Okay. Those are two branches in virtue of there being local branching at each node, the local branching in virtue of the decoherence. But the question is, why does sort of 1 go with all the ups and 0 with the downs? And why do the ups go with the downs? That's going to take us from decoherence to branches in the extended sense, which is important, because in addition to being decohered, the parts are systematically correlated. If I have up on one field degree of freedom, it's probability 1 that I'm going to have up on any other one that I measure if it's entangled with it. And if I have down on any one of the nodes, then it's probability 1 that I'm going to have down on any of I'm going to find down on any of the other entangled nodes, and probability 0 for finding up. Okay. So what makes extended branches is the systematic correlation between the values in those branches. So as I say here, in this case, every field degree of freedom carries the same record of the qubit state. So at this point, so that's sort of the answer. There's these correlations. That's what makes these into two branches, what makes there be branches, and what makes all the blue into one branch and all the red into another branch. At this point, I actually maybe have violated what I said and started to talk a little bit about interpretation. And so there's a couple of points I would sort of make here. When I say these things are correlated, what that must mean is, well, as I said, according to the Born rule, there's probability 1 that if I measure up in one site, then I'm going to measure up in another one of the entangled sites. Okay. So first of all, that's a funny thing to say because I've said we don't have any control over the field. So part of what that means is I actually couldn't do that measurement. So that's one thing that's sort of funny. More importantly, I'm invoking the Born rule here to assign probabilities to outcomes, because I need to say something about what I mean for there to be correlations. And at that point, I really am violating my rule about not going to interpretation. I think the interpretations I have in mind all agree that the Born rule is correct, but clearly they disagree about what Born rule probabilities are probabilities of exactly. So this is kind of as far as I can go without making some substantial interpretational claims. And I'm going to stop here. I'm going to just help myself to the Born rule and acknowledge I'm right on the edge of what I can say and still be interpretation neutral. Okay, good. So we know how we have entanglement. We saw how that occurs in the model. I distinguished entanglement from decoherence, and now I've distinguished decoherence from branching. I mean, branching, I should also say correlations are automatically there in entanglement. So they're automatically there in decoherence. So there's nothing that extensionally decoherence and branching have to be the same thing, but they're conceptually different. It's decoherence, but we focus on the correlations that it produces. Okay, quickly on to idealizations. So if you're thinking about, I'll go fairly quickly so we can get to non-locality. I think I've been talking for about half an hour. I want to try to wrap it up. So this will be sort of useful if you think about many worlds. I don't have time to explain it if you don't. So In real-world systems, the decoherence doesn't produce exact diagonalization. It doesn't get rid of all quantum interference, it just massively suppresses it. That's not the case in our model. Because we picked states of the field that are themselves orthogonal, we have a system where these things get exactly diagonalized. And so we don't have any tails, but they're an important feature of real decoherence and an important feature of the literature that you may know about. That's okay. We sort of don't, in a way, what we're doing here is bracketing that discussion so we can focus on the matter of the dynamics of the propagation. In realistic models, branching is a local, not global process. The world doesn't split as a whole all at once. It happens locally and spreads. So that, of course, is the thing that we're modeling here. We have local propagation, local creation of branches. Indeed, my diagram sort of shows that as the blue and the red branches slowly, increase over time. So this is exactly what we have. Ours is local because it happens discretely in time, and we only have interactions between neighbors. Also, realistically, branching is a continual process. That's not the case in our model. By continual, I mean, once a system has branched, well, it's still that branch is still governed by quantum mechanics, so there's a tendency for systems to spread, and once they spread in, become quantum mechanical, become into a superposition, well, decoherence is going to kick in again and more branches are going to form. And each one of those branches is going to spread, and then it's going to branch again. It's going to be going on and on, and it's going to be continuous. But in our model, there's only one pair of there's only one branching event, namely the interaction of the initial interaction of the qubit with the field, and then we look at the propagation of that branch. There should in reality be branches that are branching all the time. So that's also something that's suppressed here in our model. And maybe it's worth saying, one of the big issues, because of the inexactness of diagonalization, or the approximate diagonalization in reality, and the continuous nature of branching, Wallace says, and I think quite correctly, that there's no fact of the matter about how many branches there are at any time. How close to diagonalizing do you have to be to have a branch? That whole question is what we're leaving out here. It's an important question, but it's what we don't want. Okay, so I've got a couple of slides on non-locality, and then we can sort of talk. So let's sort of adopt our model to think about a non-local correlation. Well, we won't actually see the non-locality, but we'll see enough to see how it works. So let's modify the model a bit. Let's suppose we only have a finite bit of space, and we have two qubits now. One's at site 0, one's at site 5, and suppose they are entangled. So the initial state, we have a state of the two qubits that's 1, 0 plus 0, 1, which I guess I didn't write down here, but I've drawn the picture. And we want to sort of understand how the branches end up. This was our initial question. How do branches end up with non-local correlations if all the branching is itself local? I'm going to leave the qubit field interaction the same as before, but I'm going to give a slightly different interaction for the field. I don't have to. I can explain why if anyone wants to know, but it's a very natural kind of interaction. This is a unitary. This defines a unitary operator on the state space. But if I have two adjacent field nodes that are field degrees of freedom that are both up, then after there's an interaction between them, they're still both up. If they're both down, they stay both down. Well, you can see how it's got to be. If this is not going to be trivial, then the up-down state must go to down-up, and the down up state must go to up down. I'll write the equation down, but I can do it sort of graphically again. Our evolution is going to look like this. So initially we have a system where as I said, where the fields is all up, but I have one term with a 0 qubit on the left and a 1 qubit on the right, and one with a 1 qubit on the left and a 0 qubit on the right. We let each of the qubits interact with the field. According to the prescription, the 0 on the left produces a down in the first field degree of freedom. The one on the right produces an up in the first term. In the second term, one up goes to one up, and up 0 goes to down 0. Now we'll have the field terms interact, and we'll get a term that looks like this. Basically what happens is in the first term, any downs from the entangled state propagate from the left and from the right. So you can see in the first term, the down state has now propagated from from node 1 to node 2, and you sort of can't see it because the state's so simple, but the up state has propagated from site 4 to site 3. In the second term, the up state has propagated from site 1 to site 2, and the down state from site 4 to site 3. I'll draw the picture so you can see what's going on. So this is our initial state that I wrote down. First of all, the qubit interacts with the neighboring degree of freedom of the field. Okay, so I have the blue branch and the red branch, and then they interact again to produce this state. Okay, and at this point we can sort of compare. We can see that the entangled parts of the field are now adjacent, so in principle they could be measured, and we could see that they're anti-correlated. If we made the situation more elaborate and we had an ensemble and we built in that we could measure in different directions, this is the point at which they could be compared and we'd see violations of the Bell inequalities. And so we would know there was non-locality here. Our model is too simple to sort of do that experiment, but it could be extended that way. But we have an answer to our question: where did the non-locality come from? Right? Given that the dynamics is manifestly local, we just have news about the qubit propagating to the left at a finite speed and from to the right at a finite speed. Where did the non-locality come from? Not from the dynamics at all. It's really transparent here. The non-locality was there right from the beginning in the non-separable state of the qubits. We have the 1-0 correlation and the 0-1 correlation. Once it entangles with the field, that now means that we have decoherence. So in step 2 already, we have entanglement with the field. So we have the blue branch and the red branch. And each one of those branches is, in fact, both made of disjoint parts. They're made of disjoint parts, the blue part on the left plus the blue part on the right in one branch and the red parts in the other branch. And they're already anti-correlated, simply because the dynamics is, as it were, spreading the news of the initial non-separable state of the qubits. That's all that's happened here. So I think there's debate in the literature about whether many worlds is local or not. You can mean many things by local and non-local, but I think this picture makes very kind of clear what's going on, and that the dynamics in the sort of sense of the unitary quantum mechanics is indeed local. There's no extra effect. Everything is coming from, any non-locality is coming from the initial non-separability. And good. I'll just put up the lessons very quickly, and then I'm done. So first thing I did was to distinguish entanglement from decoherence, from branching. And entanglement is correlations between parts of a system. For that to amount to decoherence, it has to be that we have a lack of control or measurability of parts of the system. Those parts we would call the environment. And then branching is decoherence, but correlations. But as I said, correlations are just what entanglement is, and decoherence is entanglement. It involves entanglement. So this is just it's just decoherence, but focusing on the correlations. The step I sort of flagged was, I've talked about then what branches are. It's a further question about what worlds are. And I would say, sort of in short, what Wallace's argument would be was, okay, so we have branches. If you're a realist about quantum mechanics and you think there's only the unitary part of quantum mechanics, then you're really forced in thinking of these branches as amounting to separate parts of the world. But I won't go further into that argument. It needs to sort of think about, I think, a bit more about what that amounts to. And I've touched on then sort of EPR, non-local correlations, and pointed out how, I mean, shown very graphically how it's nothing but local propagation of non-local quantum correlations in different branches. But I want to emphasize once more that in this picture, the creation of branches, the red parts and the blue bits, is all happening locally. You can see them spreading out in these pictures. And that's all. Thank you very much for your patience.
Thank you, Nich, for nice talk. It's time for questions. If there are questions, please raise your hand and your microphone will be turned on.
Yes, thank you for your talk. I have many questions. I don't know how many of them I can ask. But my first question is that at what point do you think that branching occur? At what point, for example, in your simple model that you showed us? And can branches get zipped up and merged together? For example, in decoherence, we are really not sure if the decoherence is true decoherence or false decoherence. In quantum mechanics, things get decoherence can get to the coherence. But here, I don't see any possibility for that.
Yeah, no, that's great. I mean, one of the reasons I kind of like the model is it makes those sorts of questions sort of quite obvious, and I think, yeah, you can really sort of see what they mean and what they amount to. So the way I set things up, right, I said that in this model, the qubit, given that I'm specifying that I have no control at all over the environment and no way of measuring it, the qubit, to go back to the original, the first model, has decohered as soon as it's interacted and become entangled with the field. So that's a feature of this model. What's built into the model, of course, the model, the interaction is instantaneous, or there's just a sort of discrete, sorry, they're not instantaneous, but there's sort of discrete times. So at time one, it's now decohered because it's entangled with something over which I have no control, that I can't measure. So I think what you're pointing at is, of course, the important point that I also, mentioned, that in reality, we never go to sort of complete diagonalization. It's never completely entangled. We never have zero, we often don't have zero net control over the field. I can measure something about the electromagnetic field. So in reality, those questions are much more complicated, and that's something that, then I would just acknowledge is not sort of modeled here. So this model won't give you, it'll give you within the parameters of the model, it'll give you a precise answer for when the qubit has decohered, namely at time one. But because of its idealizations, that's not useful for saying what's happening in reality and how much entanglement and lack of manipulability is enough for decoherence. Exactly as I said, that's not part of it. The other question was about sort of recoherence, a sort of loss of decoherence. Look, and of course, that always has to be physically possible, as long as we if there's a unitary operation that takes us from a separable state to a non-separable state, then its time reverse exists formally, and if the dynamic and if further the dynamics is time reversal invariant, then there's some physically possible process that will undo all the entanglement. So recoherence is always possible, but of course, as you know, in reality, the complexity of the system means that it's very, very unlikely to ever happen. So I think that the recoherence should be thought of similarly to the way we think of the statistical versions of the second law of thermodynamics. Okay, it's not impossible. It's not strictly impossible for the entropy to decrease massively, to fluctuate to a much lower value, but it's just so improbable given the complexity of the system that it's effectively not going to happen. The same here. It's never going to happen. It's incredibly unlikely that it would ever happen that we would get branches remerging. Sorry, in the kind of generic case where we're imagining some quantum process being magnified into a macroscopic process, into a macroscopic superposition, or entangled with many, many degrees of freedom. You're quite right. There are some cases where we actually can, if we're careful, undo the decoherence, and so we have false decoherence. So yeah. Of course, there are situations like that. Sort of somehow, an example of that. And maybe you're sort of thinking as if we had a sort of if we have a massive particle, I mean, really for any mass, but if you imagine something kind of with many millions of atoms, sort of put into a spatial superposition, well, presumably it's now entangled with the gravitational field. There'll be different gravitational fields associated with each packet, but you could bring them back together, and then you would no longer be entangled. But what's important there is that we sort of don't produce gravitons. I mean, similarly, if it was charged and you move them apart, we'd have different states of the electromagnetic field. But as long as we're not producing gravitons, photons, we can bring them back together. But in terms of the model, I mean, you're quite right. It's so simple that I really can't distinguish between cases, of sort of real and false decoherence, other than by sort of stipulating that some evolutions are allowed and some are not. So I think, yeah. Insofar as your point was that this is another sort of aspect, another thing that's sort of idealized away from the model, I agree. But as I say, I think the model's useful not just for highlighting certain features, but also for illuminating certain features, but also by highlighting other features just by their absence. So I would commend it to you on those grounds too. And I've stopped speaking now.
Okay, we have 6 minutes left, and we have a few questions in the chat. Yeah, maybe I should read them loud. What is the exact meaning of field? And when you were talking about decoherence, it reminded me of entropy. Is there any way to relate these two concepts?
Yeah. So yes. So the exact meaning of field, I just mean something like sort of formally degrees of freedom associated with points of space-time. So that's all I mean. I sort of have a spin Hilbert space at each point of space-time. That's really all I mean here. That's sort of the general idea of a field. Yeah. So yes. So there are measures of entropy that would make sense here. So in quantum mechanics, for instance, we have sort of von Neumann entropy, and so this would amount to, I think, an increase in entropy for the system as it decoheres. So yeah.
Okay. The second question is, if I understood correctly, you said branching is continuous and only one single branching event. I cannot understand why is it unique.
No. So sorry, oh, interesting. Oh, it may take me too long to get back. Go back a few more. Good. So it wasn't about diagonalizing. It was about local. Yes, this last point. Good. So this is the slide where I was talking about idealizations in the model. So you have to read the bullet point at the top. I'm sorry if I didn't stress that. In the real world, branching, I've got a simple model of branching, but it's happening in the real world. Physics is making this happen in reality as well. In reality, it's happening continually. So once you imagine it's sort of a system like my setup, and it's now decohered into two branches, but each of the degrees of freedom in each of the branches is not going to stay sort of in my model, say in an up state or a down state. They start to spread into a superposition of up and down and up and down. But then those up and down components now entangle with the other degrees of freedom and so become decohered. So I had two branches sort of to start with, the up one and the down one, but they spread and decohere, and now I have four branches. There's the up down, there's the sort of over here, and then up down over here. Well, there's more. It's an ideal feature of the idealization that I only have up and down. There's really far more states here. So branching is going on and on and on all the time. There are just countless branches kind of continually being produced. And what I was saying is that is not a feature of the model. I only have like one branching event, and so I only have two branches. So something more realistic, again, there'd be more branches sort of forming off the branches all the time. Branches would be branching, and those branches would be branching in reality. And that's not a feature of the model. I hope that was okay.
Okay, thank you. And the last question is, what we can say about the relation between branch making and the problem of outcome? I guess they mean the problem of outcome in the quantum measurement problem.
Yeah, so that again is the part where I didn't want to go any sort of further. I mean, that's just an excellent question. So, the purpose, the sort of aim here is to say as much possible about decoherence and branching whilst remaining relatively neutral on interpretation, so that we can get a clear picture on how to think about branching in a neutral way, and sort of separate that off from sort of more philosophical interpretational questions. I mean, I certainly felt I wanted to understand the mathematics, the physics better of the branching framework, so that I can think more clearly about, what extra are we saying when we think that these branches are worlds, and whether that's inevitable or whether that can be resisted. Well, clearly it can be resisted. So look, I'll go back to the sort of Bohm or hidden variable kind of picture. Bohm has the unitary evolution, so these branches are forming just as I've been saying for Bohm, but because there's a hidden variable, there's something like a particle. I mean, there's many degrees of freedom, but only one of these branches is ever going to be the real one. That's the one in which the hidden variables are living. So that's a different picture about what the outcomes are, even though sort of formally these branches are all there. They're all structure in the wave function that I think the Bohmian needs to be acknowledging. So, all right, that's all about setup. I think all I can sort of say then is maybe that's it. So I think that's probably the best word I want to say. So the branching in itself leaves open different possibilities for what you think it is for the problem of outcomes. I take to be the measurement problem, and in particular, sort of hidden variables, which add variables to the unitary dynamics, and many worlds, which claims just to use the unitary dynamics. Should be able to buy everything that I've said here, but they're going to say rather different things about about the outcomes. Is there just one, or is there one for every branch?
Okay. Thank you very much, Professor Huggett, for accepting our invitation and for the nice talk. Yeah, there are some further questions, but we're running out of time. And again, thank Professor Goshen and Professor Huggett for the nice talk. We will have a 1 hour break, and afterwards we will have the talk by Professor Lutrich. See you in 1 hour. Thank you, everyone. Bye.
Thank you very much. And can I just say, if people do have pressing questions, they're welcome to email me, and I'll try to get back to people. And also, thank you very much for having me. It's been a real honor. I'm very, very happy to have done it. Thank you.
Thank you. Thank you. I hope to see you in other conferences. Bye, everyone.